Huepa! Welcome to the Caribbean, Puerto Rico. You can see the beautiful Caribbean Ocean right out there. It extends all the way into the Bay of Puerto Real over there. Not a bad location for a math class, I don't think. Certainly a great location to instruct a math course. So today we're going to continue our discussion regarding sets. Last time we looked at subsets. We're going to look at some operations on sets today, specifically 3 of them. We'll look at the complement of a set, we'll look at the union of 2 sets, and also the intersection of 2 sets. A complement of a set. Let's have a set S, and a way to denote this, because again, remember, especially on a beautiful day like this, we don't want to write out the complement of a set. So, simply the way we'll denote this is, if you can see right here, if S is a set, the complement of S is this little orange dash or mark accent right here, and we read that S prime. If this were set A, it would be A prime. If it were set B, it would be B prime. So the complement of a set S prime. Well, what is that? We're far enough along in this where we can start to see some of the niceties of using set builder notation when it comes to defining certain things. So let's look at the definition of this as we could talk about it using set builder notation. Then we'll speak more in terms of words and English, and then we'll look at it pictorially, and we'll do a few examples. But let's get used to reading mathematics. And what I mean by that is, here is a pretty good definition of what the complement of a set is. In this case, set A. So A prime, or the complement of set A, is the set of all elements X such that X is, here's our conditions, an element of the universal set. Also, X is not an element of set A. Take a moment, digest that. There's a lot of information there. A prime, the complement of A, is the set of all elements X, such that X is an element of the universal set. Also, X is not an element of A. So let's look at that pictorially. I mentioned in a previous lecture that for me, looking at math using pictures really helps. So here we have a picture that, like we've been drawing. Here we have the universal set, and keep it really simple, we have our set A, whatever may or may not be in set A. So based on this description, or this definition of what a complement is, let's see if we can kind of sort some of this out. So first of all, any element in here, any arbitrary element X, will be an element of the universal set. Okay, so everything within our space. Remember, the universal set is a set of all elements under any particular discussion. But also, X is not an element of A. So the first condition was involves everything in the space of the universal set. The second condition, X not being an element of A, would leave what area? Well, not A. So everything in the universal set that is not in A would constitute an element in the set of A prime. So all this area, with the exception of A, all the elements within here are what we're talking about that constitute the set A prime. Okay, well, let's look at some examples. We'll see how this plays out using some very simple examples. So let's let A equal the set 1, 2, 3. That U, the universal set, be elements 1, 2, 3, 4, 5, 6, and 7. So using our picture here, and our goal, of course, is to find the complement of A, or find A prime. So let's plug these numbers in so we can look at this picture with respect to this particular example. So within A, we have the elements 1, 2, and 3. The rest, the universal set, contains, of course, 1, 2, and 3, because A is what? It's a subset of the universal set. But also it's got the elements 4, 5, 6, and 7. So all elements are accounted for within their respective regions. So A prime would be all the elements within the universal set, okay? All these elements, but not the elements in A. So not 1, 2, and 3, or not what's in the red A region here. So what would A prime be, or the complement of A be? Well, we can look from the picture. It would be everything out within this region, so 6, 7, 4, and 5. And again, remember, the order doesn't matter in which we write them. And we see that as well based on our set described here. Again, the elements are 4, 5, 6, and 7, all of which we have seen from the picture. So the complement of A in this example is the set 6, 7, 4, 5. Or in other words, everything under discussion, i.e. the universal set, that is not in A. Let's look at another example. Here we have, let's set A be, again, the same set, 1, 2, and 3, and B be the set 3, 4, and 5. We want to find the complement of A. So let's draw our picture. Now this time we don't have an explicit U, an explicit universal set. But as we've been talking about, there's always a universal set. We could construct that quite easily. We won't bother doing that at this point. But we could say that U is the elements in A and B, 1, 2, 3, 4, 5. So let's draw a picture. Here we have set A. This still remains the universal set. What elements are in A? 1, 2, and 3. We have a set B. What elements are in B? 3, 4, and 5. Okay, so we see both sets share the element 3, so we can draw our picture something like that. This is B, leaving 4 and 5 as elements unique to B, elements 1 and 2 as unique to A, and 3 being an element of both A and B. So there's our picture. So what is A prime, or what is the complement of A under this scenario? Well, same thing. It'll be everything under discussion, that is the universal set. So everything within the picture, that includes B, that includes A, but it's not the elements in A. So what are the elements in A? 1, 2, and 3. So what elements are left? 4 and 5, 4 and 5. Notice it's not all of B in this particular case. There are cases certainly like that, but in this case, it is the elements 4 and 5, the ones that are unique to B. So A prime, the complement of A, in this example, would be the set consisting of the elements 4 and 5. All right, let's move on to our next, B, our next operation regarding sets. All right, now let's look at another operation, the intersection of two sets. We denote that, if we're looking at sets A and B and we want to find the intersection of A and B, we denote that with this handy little symbol, kind of like an upside down U right here. So this is the intersection of sets A and B. What does that mean? Again, let's look at a definition we could write using set builder notation. The intersection of sets A and B is the set of all elements X such that X is an element of A and X is an element of B. So let's go to our handy picture, our Venn diagram, and see if we can figure out a little more intuitively what this looks like. So any arbitrary element X we choose from the set of the intersection of sets A and B, will be an element of A. Okay, so here's A. There's A, but and there's another condition. X is also, or X is an element of B. So here's B. So condition part 1 requires X to be an element of A, but condition 2 requires X to be an element of B. Well, what region in here fits that where X is both an element of A and it's an element of B? How about here? Well, it meets the first part of the condition. It's an element of A, but it's not an element of B, is it? We could look at an element in this region. Okay, it's an element of B, but it's not an element of A. So the only region where a particular element is both an element of A and B is where it overlaps, in this picture's case, within this region here. So in other words, the intersection of A and B are the elements common to both A and B. Or to put it yet kind of another way, a little more straightforward, the elements have to be within A and B. They must be in both. That is the intersection of these two sets. So let's look at some, again, fairly straightforward examples. We'll move on to a little more interesting ones for the homework. I'll let you guys deal with that stuff. Example 1. Let's let set A be the set consisting of the elements 0, 1, 2, 3, 4, and 5. Set B consisting of the elements 1, 3, 5, 7, and 9. All right, let's draw our picture. We've got set A and B, and we want to find the intersection of sets A and B. Let's plug in the numbers in our picture so we can see how it looks. A consists of 0, 1, 2, 3, 4, and 5. B also, we can see, shares a few elements. Let's list those. B and A share 1, 3, and 5. So those will go in this middle section. Set A also contains 0, 2, and 4. Set B also contains the elements 7 and 9. Okay, so we want to find the intersection of A and B, or in other words, all the elements that are both in A, both elements of A and elements of B. And we want to do so without getting blown over by the breeze that is just picking up. So looking at our drawing, the elements here, let's arbitrarily pick this one, 2. That is an element in set A, but it's not in set B. It doesn't work. Similarly, over here, we can do the same thing. Again, the picture and the listed elements show us that the intersection, or the elements, the only elements that are elements of both set A and set B, are in this overlapping region. Namely, the elements 1, 3, and 5. So the intersection of sets A and B consists of the set where the elements are 1, 3, and 5. All right, let's look at another example. Feeling pretty good, I hope. These ones have turned out pretty nicely. Let's see if this one can perhaps be a little bit more tricky. So again, we have two sets. We have set A consisting of the elements -1, -2, and -3. Set B consisting of the elements 6, 7, 8, and 9. All right, we want to find the intersection of A and B. So let's work through this. You know what, we're getting kind of good at these. Maybe we can skip the whole picture part. Maybe we can just kind of look and see what elements are in common. Like we did up here. We noticed immediately 1, 3, and 5 were the two shared, therefore that's the intersection. Well, let's see if we can do the same thing down here. Let's see, set A, -1. Does B have that? No. -2? No. -3. Wait a minute. There are no common elements. So if we were building our set, if the intersection of A and B are all the common elements between A and B, but there are no elements, what do we do now? Does this look familiar? Yeah, this is an empty set, a null set. And this is one of the notational ways that I showed you can stand for the empty set. So the intersection of A and B, in this case, there are no shared elements. It's still a set, but it's the set that contains no elements, i.e. the empty or the null set. And again, the other notation we've been using looks something like that. And as I mentioned, both with this, the universal set, and many other things, there's all sorts of notations that are fairly common and fairly accepted, but we're just restraining ourselves to a few. So, okay, so the intersection of A and B for this example is the empty set. Well, what does that look like pictorially? What does that look like in our Venn diagram? Let's see if we can draw it. Set A, -1, -2, -3. Now set B, it won't overlap because it doesn't share any elements. All elements in B are unique to B, and all elements in A are unique to A. So, we've seen this picture before. We have two sets. Of course, all elements constitute the universal set, all elements under discussion. But in this case, we see that these two sets are separated or disjointed. In fact, that's what we call this situation. When we have two sets that are sharing no common elements, when we're discussing under the context of the intersection of two sets, when this scenario arises, we call this a disjointed set. And that makes sense. They're apart. They're not shared. They're disjointed. So let's continue our picture. 6, 7, 8, 9. So here's the picture of the intersection of A and B. Well, it's the empty set. No elements overlap. There is no common area in which they merge together. Very interesting, I think. All right, we'll have more fun with this during the homework. But let's move on to now the third and the final for now set operations that we'll be discussing, namely the union of two sets. The union of two sets. This is the last operation we'll talk about today. So again, the denotation when we're talking about sets A and B, the union of sets A and B is this symbol that kind of looks like a U. All right, so what is the union of sets A and B? Well, we can describe it, define it as such. The union of sets A and B is the set of all elements X such that X, I hope you're getting good at saying that by now, is an element, I forgot A, is an element of A, or X is an element of B. You'll notice this looks similar to our definition of the intersection of two sets, but one notable difference. The other one confined the intersection to being elements common to both sets. This one it includes the elements of either set. So let's look at this pictorially. Any arbitrary element X is an element of A, so that includes everything within the region A, the set A, or it could be any element in B, including, for this picture, what is common to both A and B. So in this case, the union of sets A and B would include all elements that are in A or B. So all this white shaded region would be the sets of all the elements we're talking about. In this case, you'll notice that we're only dealing with sets A and B, and there's nothing unique to the universal. So in this case, and in some examples, when there's only two sets under discussion and we're talking about the union, then the union is the same, is equivalent to the universal set. Now that's not always true, of course, depending on other things, but we can see where the field is expanding. So let's do some examples. Let set A consist of the set 1, 3, 5, and 10. B consists of the elements 2, 4, 6, and 10. We want to find the union of A and B. So let's use our picture, but let me erase this color. We've got two sets, A and B. Let's put our elements in. A has 1, 3, 5, and 10. B has 2, 4, 6, and 10. So are there any elements in common? Yeah, 10, one element. So on our Venn diagram, our 10 is an element of both A and B. That's the only one. So if we're looking at the intersection of these two sets, it would consist of the set of 10, but we're not. We're looking at the union. So let's fill out the rest of this. Set A also has, we took care of 10. It's got the elements 1, 3, and 5. B's got 2, 4, and 6. Okay, so what is the union of sets A and B? Well, it's all the elements in A, 1, 3, 5, and 10. 1, 3, 5, and 10, or the elements in B. Well, what's in B? 2, 4, 6, and 10. We already listed 10, no need to do it again. So 2, 4, and 6. And for this particular example, the union of A and B also is the universal set. So the union of A and B is all the elements in A or the elements in B. Let's look at another example. In this case, let A be the set 10, 20, 30, and B be the set 5, 15, 25. We wish to find the union of sets A and B. Well, it's all the elements in A, 10, 20, 30, or all the elements in B, 15, 5, and 25. Okay, so that's the set A union B. But as we're writing those, we may have noticed something. Let's draw a picture. In fact, we looked at this picture just a little while ago with our example with intersections. There are no common elements between sets A and B in this example. All three elements of A are unique to A, and all three elements in B are unique to B. So the picture we saw looks something like this. So we have A, here we have B, A 10, 20, 30, B 5, 15, 25. The intersection of this would have been what? No elements in common? Yeah, the empty set. But the union is all the elements in A or all the elements in B, including any that may overlap. So our union is not the empty set like the intersection was. Rather, in this case, it's the universal set. It's all the elements in A and all the elements in B. So we see the same picture, but two very different sets based depending on our operations of union or intersection. All right, let's work on a few more examples together, and then I'm going to give you some homework that I think will really help you with this. All right, we've looked at our three operations. Now let's look at some examples in which we can see all of these at play and get a little bit better, a little bit more used to seeing some of these different situations. So for this example's sake, let's set A consists of the elements 1, 10, and 5, B the elements 1, 2, 3, 4, and 5, and C the elements 3, 5, 7, and 9. I've taken the liberty to draw the Venn diagram that could represent this. You'll notice by observing these and the Venn diagram that A has an element unique to it, 10, B has two elements unique to it, 2 and 4, and C has two elements unique to it, 7 and 9. A and B have a common element 1 and 5. Sets B and C contain the common elements 3 and 5, and sets A, B, and C together contain one common element, 5. So let's use this example and find and go through the various operations that we've been looking at. So first of all, we want to find out what A prime is, or what the complement to set A is. So first of all, let's construct the universal set here. We have the elements 10, 1, 5, 3, 7, 9, 2, and 4. Of course, we see that here with all the elements under discussion. So the complement of A would be everything in the universal set, but also not the elements of A. So what are the elements of A? 10, 1, and 5. or everything under discussion not in A. So that would leave the elements 3, 7, 9, 2, and 4. And again, we can observe that all the elements in the universal set, without those in A, that includes 2, 4, 3, 7, and 9. Excellent. So the complement of A. All right, let's try the same thing with the complement of B. So the complement of B will be all the elements of the universal set, basically without or with exception of those elements in B, or all elements not in B. So here we have B. We have the elements 3, 5, 1, 2, and 4. All other elements in the universal set that are not contained in B, 9, 7, and 10. 9, 7, and 10. So the complement of B consists of the elements 9, 7, and 10. Not too bad. Let's look at the complement of C, or again, C prime. All right, all the elements in the universal set that are not in set C. I'm trying to say this in multiple different ways. Here's all the elements in the set. The ones that are not in C, well, here's C. So all the elements left, we have 4, 2, 1, and 10. So the complement of C consists of the set of elements 10, 1, 2, and 4. All right, very good. Let's look at the other operations that we worked through. Let's start with the intersections. The intersection of sets A and B. Remember, those are the elements common to both sets, in this case, sets A and B. So what are the elements common to sets A and B? And we can work through this up here, or both back and forth. So the elements common to A and B, this is what makes these Venn diagrams so nice. It really pops out. If here's set A, set B, the elements common to both of them would be in this kind of I-shaped region, O-ho-shaped region, 1 and 5. They're elements of A and they're elements of B. And only two elements in this case fit that criteria, namely elements 1 and 5. So the intersection of sets A and B is the set consisting of the elements 1 and 5. How about the intersection of A and C? Here's A, here's C. The elements common to both of those, well, just 1, 5. So the intersection of A and C, in this case, is the set of the one element 5. And let's take a moment to compare up here. If we look at A and C, what elements are common? 1, no. 10, no. 5, yeah. And that's exactly what we got from the picture. So it's helpful to work both ways on this. All right, let's look at the intersection between sets B and C. Let's start up here this time and then compare with the picture. So sets B and C, we want to find the common elements, or in other words, any arbitrary element X that we choose out would have to be an element of B and also C. 1, no. 2, no. 3, yes. Any others? 4, no. 5, yes. So the intersection of B and C should consist of the set 5 and 3. Let's look at our Venn diagram and see if that's what it looks like there. So B and C, the two elements that are common to both, again, we see 5 and 3. Very good. All right, let's look at now the unions. Let's start with the union of A and B. We'll start with the Venn diagram. So remember this one, the union are all the elements in A or B, including elements that might be in both A and B. So all the elements in A or all the elements in B constitute the union of A or B. So let's list all the elements in both of those. Let's start with A. We have 10, 1, and 5. Okay, we're not done because we're dealing with union, so we have all the elements in B as well. We already got 1 and 5, but we also have 3, 4, and 2. All right, a pretty large set. You can see how these unions get large fairly quickly. Let's look at the union now of A and C. And this time, let's start up here. So all the elements in A or the elements in C. So we have all the elements in A, 1, 10, 5. All the elements in C as well, 3, 5, we already got, 7, and 9. Let's check our Venn diagram, see if that matches our picture. So all the elements with A and C, or the union of A and C, should consist of the elements 10, 1, 5, 3, 7, and 9. But what about these two loner elements? Why do we leave those two out? Well, because they're unique to B, and this is the union of A and C. All right, let's try the union of sets B and C. Should consist of the elements 4, 2, 1, 5, 3, also 7 and 9, because that's part of C as well. So the union of B and C would consist, or is the set consisting of the elements 1, 2, 4, 5, 3, 7, and 9. Let's check up here. B and C, we have the elements 1, 2, 3, 4, 5. Excellent. Then all the elements in C as well. 3 we already have, 5 we already have, 7 and 9. Very well done. Now we're going to do just 2 more examples before I turn you loose on the homework, but they're a little bit more involved. Here's our next example to work through. You can tell it's a little bit more involved. We're looking at the union between the sets B and the set that is the intersection of sets A and C. We'll have fun with this. Now, before we get going, we'll talk about order of operations a little bit later in a few lectures. But right now, I'll just list a few that are relevant to what we're doing. If you remember order of operations, you work, when you look at a mathematical expression and you're simplifying or solving for, whatever you're doing, there's a few rules that you follow through to make it work. One is you read from left to right. Or I guess you guys would be looking at, let's see, your right to left. If you're looking at the board, my left to right. If you're looking at your paper, left to right. Or in other words, this direction. That's a little simpler. So you work this direction, but you start with what's in parentheses. Here we have parentheses. So even though we work left from right, we would first look at whatever this is. There's parentheses, so we start by working with what is included within those. So the first thing we'll have to look at is the set that is the intersection of sets A and C. So for now, order of operations, 2 things to remember. Work from left to right, this direction, and begin with what's in the parentheses. So what we are looking for, this is going to be equal to, that's our goal, is to find out what this whole conglomerate mess or fun activity, depending on how you look at it, is going to equal. What set is it going to constitute? We're sticking with the same sets A, B, and C as we used in the previous examples. So let's begin with what's in the parentheses. We're looking for the intersection of sets A and C. Well, we have A and C. Remember, the intersection are the elements that are common to both. A and C, well, we simply have one. We have the element 5. Let's check it up here. A and C, Yeah, 5's the only element that is common to both sets. So, let's keep track and keep order here. We're looking at the union of sets B and whatever this turns out to be, which we noted is simply the element 5. We're good on that. The intersection of A and C is a set that consists of 5. Okay, but we're not done yet because we still want to find out the union between set B and the set, which is the intersection of A and C, which we're listing as the element 5. We want to find what that is. So remember, the union are all the elements in both respective parties, in this case B. So what's in B? 4, 2, 1, 5, and 3. 4, 2, 1, 5, and 3. Okay. Or in set 2, in this case it's simply the element 5. Well, we already have that, so we're good. So the set described above consists of the set 4, 2, 1, 5, and 3. In this case, set B. All right, let's try another one. Here's the last example we'll look at together. We're looking for the set that describes all of this. Now, we're going to begin by working left to right, beginning with parentheses. So we're going to focus on everything in here first, but there's also kind of another embedded operation going on, namely this A prime, or the complement of A. So we're going to have to start, this is almost like a parenthesis within a parenthesis, we're going to have to start by figuring out what A prime is. Okay, so the first thing we must look at is what is A prime. And we're going to list our information a little bit differently this time. I'm trying to give you a few different ways to organize yourself. Last time we kept everything within the expression and work downwards. Now we have a few more pieces to find out, so we're going to kind of make a column and keep track of things that way. The first piece of information we need to find is the complement of A. So, what is the complement of A? Well, it's all the elements in the universal set, but they're not elements of A. So if this is A, 10, 5, and 1, all other elements would include 2, 4, 3, 7, and 9. So A prime is the set of elements 2, 4, 3, 7, and 9. All right, so this is what is included here. So now we're looking at the intersection of B and A prime. Well, here's B and A prime. So let's keep track of our information. Okay, remember the intersection are the elements common to both sets. So what are the elements common to B and A prime? Well, B is fairly obvious to see up here, and A prime we've already figured out. That's why it's nice to write it out. So let's see what elements are common to both. Does B has a 1. Does A prime have a 1? No. B has a 2. Does A prime have a 2? Yes. So 2 is common to both. How about 3? Yes. How about 4? Yes. How about 5? No. And we're done up there. We have 7 and 9 not common to B. So the intersection of B and A prime is the set consisting of the elements 2, 3, and 4. Now our picture, this kind of makes sense if you can kind of keep track of all this in your head. What is common to B that is common to not A? Well, here's A. So what is common to B and the rest of it? 2, 4, and 3, which is exactly what we have there. So this is the first part. So we can reduce this to this set right here. 2, 3, 4, Okay, but we're not done yet, are we? We still need to find the union of this with C, and that will give us our final answer. So remember, the union are all the elements that are in set 1, in this case C, or are in the set, in this case, the intersection of sets B, A prime, have a mouthful, this set here. So all the elements in here and in C, and that will be the final set that this whole expression is describing. So let's start with set C. What elements are in C? Well, 3, 5, 7, and 9. And what elements are in this expression, the intersection of sets B and A prime? 2, we don't have a 2. 3, we do have a 3, and 4. So this set lists the elements that this whole expression is describing. So let's write this kind of in a final form so we know what we're saying. So we're saying expression is equal to, or is the set consisting of the elements 3, 5, 7, 9, and 2. Very good job. That one was a little bit challenging, I think. So here's something. The way you could describe the set consisting of these elements is by using this expression. All right, now we're going to look at, I'll give you the homework. Now, homework is very important for this assignment. We can go through these on the board, and you can follow on the board and say, oh yeah, I know what he's doing. I know I'm with him. But when it comes to do your own, there's a lot of different sets and a lot of different scenarios that we could come across. We're only going to work with 10 of them. But it's very important to do these on your own because you'll encounter things that we didn't talk about. I mean, we went through the principles of them, but you'll come to scenarios, situations that you'll have to wrestle through thinking about what these operations are. So I'll give you homework. It's very important. There's only 10 problems. Some are fairly easy. Some are a little bit more involved, a little bit more complicated. And next time we get together, we will work through them together. Maria's just let me know that she is really excited to work through all of this homework. So I hope you share her enthusiasm as well, although I'm not entirely sure if it was sincere or sarcastic. But regardless, the homework is where the learning takes place. So, our homework assignment for this lesson, find the following. Here's our sets. We'll let set A be the set 1, 2, 3, 4, and 5, B 2, 4, 7, 9, C 6, 7, 8, 9, 10, and set D the elements 7, 4, and 11. There's 10 different scenarios, 10 different expressions that we want to find the set that these scenarios describe. Notice I forgot to put equal signs after all of these ones. So I won't read these aloud. I'll leave this on the screen for a while so you can copy them down. But I do want to point out, just highlight the prime symbols for the complements in case they may get missed. Here we have a prime. This is the complement of C. Here we have a prime, another complement of C. I did that to be nice because once you find out the complement of C, you already have done that part, then you simply have to do this part. Hint, hint. Keeping track of information helps a lot. Here's a prime for B, the complement of B. And here, this one's interesting. The complement of the empty set. Prime right there. And then we have 2 in this one. A prime, the complement of A here, and then B prime, the complement of B there. Very good. I look forward to working through these with you in our next time together. It's starting to get cloudy here, so I think it's time to bid adieu. I'll see you next time. Have a great one.
Thank you for learning with the Fosters. This is a friendly reminder. Remember that these courses are not for free. For information of the cost of the lessons and how to pay, please visit our website. Thank you so much for being with us.